Thank you, Marcy, and thank you everyone for joining us. Hopefully all of you are enjoying your day and are eager to learn about the upcoming changes in the 2015 wind and seismic provisions. Okay, let me see, my remote isn't working, so I will have to use the arrow key. Okay, now let me check. Okay, the remote wasn't working at first. Okay, this presentation is copyrighted with American Wood Council. If you'd like to use any portion of the presentation, please contact us directly and we'll help expedite that. Also, new to our education is the AIA Continuing Education. This presentation is registered with AIA. As Marcy mentioned, if you're seeking AIA, we will need your AIA number to register you with the organization for continuing education. And for those of you that have downloaded the PDF of the presentation, here's a description that is included in the PDF for later reference, and we have our learning objectives. And today we're going to talk about being able to understand load path basics and how it applies to wood structural design. We'll also look at the significant changes from the 2008 to the 2015 wind and seismic provisions. And then you'll be able to identify lateral resisting systems and understand how to obtain design specifications. Additionally, you'll be able to apply, sorry about that, formal content, understand the content and the overall organization of the wind and seismic provisions. Okay. Now for our first poll of the day. This one's a pretty easy one. Hopefully you can participate, and we'll have Marcy launch the poll.
All right, what is your profession? Are you an architect, engineer, code official, building designer, or other? Go ahead and vote. As always, I usually close the poll at around 80% or at about 30 seconds. So. All right, about 85% of you have voted. I'm going to go ahead and close. And the majority of you are engineers, 75%, some code officials, 16%, and a little bit of architects and others. Oh, and 1% building designers. So glad that you are all here and joining us. And Michelle, I'm going to give it back to you.
Great. Thank you, Marcy, and thank you everyone for participating. It's understandably that most of the people in the audience are engineers, but we're glad to have all of you in attendance to learn more about designing for wind and seismic loads. Now, as an overall outline of the presentation, we're going to look at some overall lateral load basics, the systems and what's involved for providing the continuous load path. Then we'll look at the code acceptance, how it's been adopted in the code, and then we'll do an overview going chapter by chapter and looking at the significant changes from the 2008 to the 2015 wind and seismic provisions. And then at the end, well, when that'll be divided up into the first 3 chapters of the wind and seismic provisions, and then Buddy will take over at the shear wall section of the presentation. And then at the end, he'll summarize the top 10 or 11 changes that have occurred. Now, jumping into this, I want to say that throughout the presentation, we'll go through the slides, and some of these slides will have a lot of text. The reason that text is in there is to look at later on to get in more depth information, but we'll go over an overview of the text that's in that slide. But as I mentioned, we'll start off first with some load path and overall system for seismic and wind resistance. Now, when we design a building, we have 2 basic lateral loads that we design for. One is wind and one is seismic, earthquake motion. And for those of you, and I've said this in previous presentations, when you have, sometimes you're dealing with designs, architectural designs, that don't necessarily could physically work because they don't have a continuous load path. Now, there's a section in the code 1604.4 that really requires us, and basically physically it requires us to have a continuous load path from the point of origin of that load to the lateral existing system. And when we look at wind loads are applied in this illustration right here. We have them in the left to right direction diagonally. We have a wind pressure that's applied to the windward walls, and the studs span from the foundation to the roof, and then also the wind continues across that roof system, applying more force across that roof system. And then also on the leeward walls, we have the wind that pulls on those walls at the end. And the roof acts like a diaphragm that spans like a big beam to the vertical lateral resisting system, which is typically your shear walls. And if we look at a square building, a different illustration, we would see, again, the wind that will apply pressure to those studs, and then the diaphragm acts like a deep beam that spans from shear wall to shear wall that resists that loads. Now when we're dealing with seismic loads, it's actually the earth that applies that force to the building, and that building wants to catch up. And a lot of that deals with force equals m times a, the mass of the building that resists that load. We idealize it as if the lateral load is concentrated or applied in the roof diaphragm, and then similarly to wind loads, that roof diaphragm acts like a deep beam and transfers the load to the shear walls. Now if we get a plan view of the diaphragm, we would see that a uniform load on the diaphragm, it acts like a deep beam. We have the chord forces, compression on the top and tension on the bottom. And then we resist that load. The diaphragm transfers that load to the shear walls. And the reaction goes to the shear walls. And then if we're dealing with seismic loads, and in seismic design category C through F, we are required to have continuous ties. And we'll get more into this when we're talking about diaphragms that resist masonry and concrete heavy wall loads. Which is something new to the wind and seismic provisions, but we'll go into this in more depth later in the presentation regarding continuous ties and struts. And the basic structural elements of the building are going to be basically your diaphragm, which is in the horizontal plane, then has collectors to provide a continuous load path. And then we have shear walls, your vertical lateral resisting systems, and those also have drag struts or collectors to make it to continue the load path to those elements. If we're looking at diaphragms, we can idealize those diaphragms as if they are flexible or rigid diaphragms. And we'll go into that later in more depth later in the presentation, because this is one of the areas where we've made some changes to the wind and seismic provisions regarding transferring the horizontal force to the vertical lateral resistance system, and how that looks like when we're dealing with flexible or rigid diaphragms or semi-rigid diaphragms. But we can categorize, or idealize the diaphragms as flexible, and flexible diaphragms transfer that horizontal load based on tributary area, whereas a rigid diaphragm transfers the load based on the stiffness of the walls, and there's a torsional component to it as well. But looking at in a very simple diaphragm that shows the stiffness of the walls, we have a uniform load on the top, which is a W, and then we have certain stiffnesses of our shear walls. The outer walls have a stiffness of 2 times the interior wall, which is 1K. And if we base the distribution based on a flexible diaphragm, we would see that 25% of the load goes to the outer walls, just based on pure tributary area. So 1/4 of the loads goes to the outer walls, and half the load goes to the inner walls. Whereas a rigid diaphragm without torsional component, we just base it based on the stiffness of the shear walls, we would see that 40% of our load goes into the outer walls of each of the outer walls, and 20% into the interior wall, because we have a stiffer wall on the outer exterior walls. Now we'll get in more into this later on in the presentation when we talk about horizontal distribution, but this gives you an overview of how the loads are transferred between the two different flexible and rigid diaphragms. There's quite a bit of difference in the actual load when you're designing them the two different ways. And as I mentioned previously, we talked about having a continuous load path. We're looking at a typical layout of a load in the north-south up and down the sheet, and the shear walls involved. We have some walls on the left, and then in middle shear wall, and then one on the right. And in the east-west direction, we would have a similar layout of shear walls. Now the key is we want to be able to transfer the load from our diaphragms and make sure that that load gets transferred to the shear walls. And that's where we incorporate the collector beams that can be in the plane of the floor. In addition, we can have also, we'll require to have some type of drag strut to make sure that the load is transferred within the line of the shear walls to make sure we get distribution to those walls. Now, if we're looking at a section of a drag strut within the roof diaphragm, we would see a collector beam, making sure that that collector beam is nailed off, and that's very important, nailed off from the diaphragm to the collector beam to transfer that load. Similarly, in the plane, in the wall plane, if we're treating this as segmented shear walls, where we're just looking at the full height shear wall, we would need some type of collector to make sure that the load gets transferred to these shear walls. And a lot of times it's just the top plates, or we could have the headers acting as a drag to connect it to each other. Now, going back into basics regarding the shear walls, we would see this is just a typical shear wall. It's a 4x8 shear wall. The 5 parts of the shear wall. We have the wood framing that makes up the skeleton of the shear wall. And then we have the wood structural panels and the nails. Now the wood structural panels and nails provide the stiffness and strength to that shear wall to resist the loads that we want to resist. Then we have the anchor bolts and the plates, the washers or connectors at the bottom of the plate that transfer the load from the top. Well, we start off with the load at the top of the wall. It gets transferred through the framing and the wood structural panels and the nails to the bottom of the wall that gets then transferred to the foundation through those anchor bolts and plates. And then to resist overturning, we have hold downs that resist overturning, because when this load is applied, the load wants to overturn that wall. Now there is a difference between the language or the vocabulary of uplift and overturning. And I think Buddy will get into this later in the presentation when he talks about overturning, but for those that are used to designing in seismic areas, they tend to say that there's uplift on the end of the hold down, and there's a different uplift also that we design for, and that is uplift of the building because of the uplift of the roof. We'll look at that later in the presentation. But the overturning of the shear wall is resisted by the hold down. And I'm sure Buddy will clarify this. Now, if you look at this slide, we have on the right a picture of an 8x8 shear wall that has a panel joint in the middle, and this shear wall had some seismic tests done using Curie's cyclic protocol, and on the left you would see a graph that shows the results of the testing that was done. The cyclic testing, there's some load applied. The load is on the vertical axis, and then there's a displacement. And what the unique ability about wood construction or wood shear walls is its ability to displace quite a ways without failure. And you can see from this graph we're at the maximum strength of here at the peak load, and hopefully you can see my cursor, but there's a peak, oops, sorry, I just went backwards. Let me just get the pointer just in case. Someone, if you could tell me if you're seeing my, I don't know if you're seeing my cursor, but at the peak load, you would see it displaced 3 inches. That's quite a bit of Yep, you can see it. Thank you for answering. Okay, so at the peak load, you can see it's over 10,000 pounds, and it's displaced 3 inches. That's quite a bit of distance for displacement, and still without failure. And then right about 1 inches, you would see that this is the design strength that we designed for, and that's about 3 times less than the peak strength, which is great, what we've seen. Now, after we've reached the peak load, you can see that the strength, the shear wall, has reduced in the resistance that it can, something around somewhere between 10,000 and 5,000, I think that's 5,000, where its resistance is less, and there's been a failure here. It's displaced over 3.5 inches. So this is where something has failed. We've had some failure in it, whether it be the panel pulling away, nails pulling out through the panel, or withdrawal from the framing. Now, the one thing I want to point out is when we're dealing with shear walls, we have a lot of nails, a lot of connections. And if you think about that throughout the building, if you have multiple shear walls, multiple diaphragms, and all of that nailing, all of that connection and all of those nails actually provide the ductility in the system, and for it to be able to resist these loads and displace without failure. And later on in the presentation, when Buddy talks about shear walls, one thing I want to point out is the detailing that is incorporated in the wind and seismic provisions that will help mitigate about some failures that we've seen in the past through past earthquakes. And that has to do with the sill plate connection. We found that through going back to even Northridge earthquake, or maybe even before that, there was some challenges with the sill plate, whereas when that shear wall wants to resist shear or lateral load, there will tend to be an uplift of that panel on the sill plate, causing cross-grain bending, which is a challenge, because then you're not dealing with a ductile failure. Also, the panel joint that you see, these are two 4x8 panels. The panel joint, there were some challenges here with pulling out. Well, I'll show you here. Where previously, if there was heavy nailing and there was only a one stud there and a lot of nailing, there can be some issues there. But Buddy will mention this later in the presentation. But some typical failures shown here is for the picture on the left, we have nail yielding at the adjoining panel edges, and then also the picture on the right, we have nail yielding where the head of the nail is pulled through the panel, and also that we've had the nailing on the left where it's pulled away from the framing. But the great, I guess you can't call it great, but the mode of these failures is the nail yielding, which is what we want. We want a ductile failure. We don't want a brittle failure. And then, so Bunny will mention this when it gets into the detailing requirements. A little bit of background. Also, in the wind and seismic provisions, there are 3 types of shear walls that are covered in the wind and seismic provisions. We have the individual full high segment walls, which is what has been used throughout many years of designing shear walls, where we're dealing with a hold down. Here on this end, we have a shear wall here where there's a hold down here and here. And then there's a shear wall here with a hold down here and here. And we don't take into account any of the stiffness or strength that's provided for, or especially the stiffness that's provided for if there's panel above and below the opening. So we're just treating this as full high shear walls. 2 other methods of designing shear walls is a force transfer around openings and the perforated shear wall. And that is where we look at the entire shear wall here. We can eliminate the hold downs in between, and we design this as if it's one entire wall. And we take into account the stiffness that's provided by the sheathing, and that means that this whole entire wall is has wood structural panel or whatever your shear wall is along the whole entire wall. And if we're dealing with that, we're dealing with force transfer around openings. There's no prescribed method of analyzing these types of walls based on principles of mechanics, and there's detailing required above and below the openings to assure that the loads are transferred above and below that openings. And then the perforated shear wall method is based on empirical testing that was done for those shear walls. Some additional anchorage may be required on the bottom sill plate and a shear adjustment factor also that's applied to the shear wall capacity table values that Buddy will mention later in the presentation. Okay, now how is this adopted in the code? Well, in the 2000 IBC, which many of you may be on, the 2008 is reference document for the wind and seismic provisions in the 2012. It's not till we get to the 2015 IBC that it adopts the 2015 wind and seismic provision. So that's how it's adopted. And then all previous, I believe, even 2006 and 2009 adopted the 2008 also as a reference document. Now, what does the wind and seismic provisions cover? Well, the provisions cover the materials, design, and construction of wood members, fasteners, and assemblies to resist wind and seismic loads. And it includes both a dual format ASD and LRFD. And we'll point these out throughout the presentation on the differences. Here's an overall outline, but Chapter 1, we'll go through each of these chapters, and I won't go into in detail, but there's 4 main chapters through to the wind and seismic provisions. Now, the first chapter is very basic. It's our design flow chart, and that is just what is the philosophy or how this is created is that you assume a trial design. You decide what method you want to use, ASD versus LRFD. You go down the path, and hopefully you have your capacity of your system is less than your demand. If it's not, then you do a reiterative process and try a new design. Now, general requirements is in Chapter 2, and this is where we get into our terminology, our notations, the abbreviations that are used throughout the wind and seismic provisions. And one section that is new to this is added new to the 2015 wind and seismic provision is this section 2.1.3, and it has to do with sizes. Now, and it's to incorporate the language for we use nominal panel thicknesses when we're providing these provisions. And it has to do with the nominal as it relates to performance category nomenclature of PS1 and PS2, and that we all know panels when they're manufactured very dry, and then when they get to the job site they tend to acclimate, and the thickness of the panel does change with the environment that they are in, where they're in service use. But this section just is to provide that charging language that what is assumed is that we are using nominal panel thicknesses in the design provisions. Okay, now also new to Chapter 2 are definitions. If some of you are familiar with using the 2008 wind and seismic provisions, you know that we had a section for open fret diaphragms and cantilevered diaphragms. They were actually 2 separate sections. Well, throughout the research that has been done through ABWC and through the technical committees for this new 2015 provisions, we've determined that there's actually, when you have an open fret diaphragm, it's actually a structure in which any diaphragm edges cantilevers beyond a vertical elements of lateral force resisting system. So they're one and the same. They're not 2 different systems. So one definition, and if you know that in the 2008 there was never a definition of open fret diaphragm either. There was a section that was called that, but never a definition. Additionally, we've added a definition for subdiaphragms, and subdiaphragms is a portion of the diaphragm used to transfer wall anchorage forces to diaphragm cross ties. And this diaphragm was incorporated because we have a new section that covers subdiaphragms related to anchoring of heavy walls, such as concrete and masonry walls, into the diaphragm. And we'll go into that later on in more detail later in the presentation. We've also removed the definitions for flexible and rigid diaphragm, and this is to avoid conflicts with the definitions that are in ASCE 710, and also to also go along with not only what's in ASCE 7, but also because you don't really have a flexible or rigid diaphragm, you can idealize it, and that's the language we'll use throughout the wind and seismic provisions, but you can idealize it as a flexible and rigid diaphragm, and we'll show you how you can do that throughout the later on in the presentation. More to come. Chapter 2, Design Methodologies. As I mentioned previously, we have 2 design methodologies. One is ASD and one is LRFD. That's not a change. One other thing that I should note is throughout the presentation you'll see these 2 icons here. We'll have the 2008 and then the 2015. If there's something that I'm presenting that applies to both, you would see 2008 and 2015 icons. If it's a change in the provisions, then you would only see the 2015 icon in the slide. So just another illustration to make it clearer. Now we're getting into Chapter 3, which is the members and connections. And this deals with your framing, your sheathing, and your connections, as well as those members that are resisting out-of-plane loads, your diaphragms or the sheathing for the walls, and we'll get into that. But this is a section that you would go to for out-of-plane and individual framing and connections, as stated. One change that has occurred for the wind and seismic provision has to do with the repetitive member factor for wall studs when we're designing our wall studs for out-of-plane loads. If wind is being applied to that framing system, then it needs to resist flexure and out of plane, or resist a load out of plane. Now this repetitive member factor accounts for a composite action that occurs because we have a wall stud that is nailed off for the wood structural panel, for example, and then also there's some assumptions that it's also connected to the gypsum on the other side, and those assumptions are spelled out in this section. But there is a composite action that occurs because we have all of those members acting as a system together. Well, what's new to this section is not only can you apply this to the strength, your flexure resistance, but you can also apply this to the stiffness when you're checking the deflection of that wall stud to resist. And if you have a brittle finish, say, and you've got to check that stiffness, this repetitive member factor can be applied to that. So now not only strength but also stiffness, your EI. In addition to that, what's new is we've increased the spacing of the studs from 16 to 24 inches. So this can be applied to 24 inches on center as well. Also, a revision has occurred to the out-of-plane. This table covers the nominal uniform capacities for wall sheathing that resist out-of-plane wind loads. From previous to the 2015, in the 2008, the capacities of the sheathing was based on a 3-ply product, whereas now, unfortunately, well, it was found that it was impractical to manufacture 3-ply, and there are no longer those panels for 3-ply that are commercially available. So now the values are based on, for the 4824, they're based on a 4-ply panel. So now you have a panel that's got more stiffness, and more capacity, and you'll see an increase in the values based on this. Similarly to the out-of-plane wind loads for roof systems, similar, that we've had an increase in the capacities because now we're not basing it on a 3-ply. It's now a 4-ply or a 5-ply, depending on the span rating. So new to the system. Now we're going into looking at uplift forces. I mentioned in the beginning there was a difference between uplift and overturning. When we're dealing with uplift of wind loads, we have an uplift on that roof, and we need a system to resist that uplift load that will carry all the way down through to the foundation. In areas where we don't have high winds, we may not even need to consider this, because if we have a really heavy tile roof, there may not be a net effect of uplift on that roof. But for those areas that have that net effect, that load has to be transferred all the way down to the foundation. What's new to this now is a section 3.4, which covers the continuous load path of that load, taking it all the way down to the foundation, and provides charging language that you need to provide that continuous load path that is adequate, not only in strength but stiffness, to resist that load that's uplifting. And also, it also forces on when there are some eccentricities in that system, that needs to be taken into account in the design of the system. And I'll get more into that in this slide. So we have uplift of the rafters. That uplift needs to be resisted. We need to provide a continuous load path down all the way to the foundation, to whatever system you provide. In this illustration, we all have some straps that continue connecting the studs, and then additional straps where there's a discontinuity in the framing system. Well, when I mention about eccentricity, sometimes what happens is, and actually this may happen a lot, is you may have an eccentricity in your load path because the studs don't all line up, or your rafters don't all line up all the way down. So if there are some eccentricities in that load path, that needs to be taken into account in the design. I mean, you could specify that they all align, but you may run into some issues. Okay, now on to really the bulk of what we want to talk about, having to do with our lateral resisting system for resisting that resists the loads in plane. This is where we talk about our diaphragms and our shear walls. And as I mentioned, when I'm through with the diaphragms, Buddy will take it from there on the shear walls. So this section talks about, I just said it, we talk about wood diaphragms and wood shear walls, and those that resist in-plane loads. Now, diaphragms, that's what we'll get into. Hopefully all of you are still with me. Okay, now when we talk about, I mentioned earlier the introduction of the definition of sub-diaphragms. In ASCE 7, we have a section 4.1.5.1 that actually, that's not the section for ASCE 7, that's the section for the wind and seismic provisions. But there are sections in ASCE 7 that covers the concrete and masonry walls that resist loads out of plane. And this section was introduced to provide some language that, yes, you need to design for that load out of plane. And in this illustration, it'll become more evident on why. When we're dealing with seismic loads, what happens is if we have diaphragms that are spanning from shear wall to shear wall, these concrete walls will tend to want to pull away from the diaphragm when an earthquake occurs. And it's very important that that wall is anchored into the diaphragm enough so that it can resist the loads in the diaphragm, and then eventually transfer that load to our shear wall. And that occurs in the opposite direction as well. And this is very evident in past earthquakes where there has been some failures on buildings where they weren't adequately anchored into the diaphragm, and then the wall has pulled away from the diaphragm and you'd have a collapse of the roof. And Marcy mentioned that we are going to have a special webinar in June. Hopefully all of you will sign up. We'll have John Lawson that'll be actually presenting on this whole very concept of anchorage and how to develop the load into the diaphragm. And that'll be mentioned. If you missed that, Marcy will mention it again later in the presentation. There are two different basic types of diaphragm. We have an all-wood diaphragm or a hybrid diaphragm that use steel bar joists. But the whole philosophy or what we're talking about is if you have a wall, and I should have had a better picture, but we have a wall on the left side that we want to anchor in through these subpurlins into the diaphragm to develop the load enough so that it can transfer that load to a larger diaphragm that then can transfer that through to the shear walls and across, also tie across to the other side of the building. But we would anchor perhaps maybe every other subpurlin and then continue tie and then develop your diaphragm loads within here so it transfers this sub-diaphragm to a larger diaphragm that has a tie across the building. And here's a detail of that, showing that. Now the one thing I want to point out is that for diaphragm loads, when we anchor this wall into this purlin, we want to have an anchor on each side of this purlin to prevent eccentricities that can occur if it's only loaded on one side. Additionally, we want to nail off this diaphragm to the purlin to make sure you're developing that load into the diaphragm, and then provide continuous ties across more. Especially in seismic design category, I think I mentioned C through F, or maybe it was B through F earlier in the presentation. Here's another example of a tie that's anchoring this either masonry or CMU or concrete wall into the diaphragm. And what we don't want is this here, which has occurred in previous detailing, and that is that what happens is, since they're not tying this into the diaphragm, this can cause some cross-grain bending in this ledger, which has caused some failures in the past. And so we don't want this type of system. What we want is to have it tied into the purlins or sub-purlins to drag that load into the diaphragm and develop it into the diaphragm. So this is a new section, charging language, that covers this type of design. Now we do have a poll coming up.
All right, let's go ahead. The 2015 seismic and wind and seismic provisions for anchoring concrete or masonry walls to wood diaphragms requires continuous ties or sub-diaphragms for continuous load path, or applies to seismic design categories A through F, or are not referenced in the ASCE, or none of the above. Go ahead and vote.
That was a mouthful, wasn't it?
It was a mouthful.
Sorry, Marcy.
That's okay. Need a little challenge, especially this was a long break, so. All right. Almost 80% have voted, just a few more of you. All right, I'm going to go ahead and close. All right, and share. 93% say the requires continuous ties or sub-diaphragms for continuous load path. 3% say apply to seismic design categories A through F. 1% are not referenced, and 3% none of the above. And Michelle, the real answer is?
Okay. Okay, the real answer is continuous ties and sub-diaphragms. Requires continuous ties and sub-diaphragms for continuous load path. And it does not apply through to categories A through, what did I say? I have to look at my notes. Even I, so for those of you, it does not apply to category A. I believe it's, and you can, I can't remember, it was C through F, I believe, or D through F, A, B, C, C through F. It is referenced in ASCE 7, and it is So the correct one is, it is some of the above. The correct answer is A. Okay, now, but most of you got that right, so that's great. We're communicating clearly, hopefully. Okay, now, wood diaphragms. We have wood diaphragms, and in section 4.2.2, we have the deflection equation, which is now a three-part equation, and actually it was a three-part equation in the 2008 Wind and Seismic provision. The three parts of the equation is the first part deals with the bending, core deformation, excluding slip. The middle term includes shear, which is the panel shear and nail slip. That combine the two inner terms of that equation from the four-part term equation. And then we have the last term that covers bending, which includes the chord slip. Chord slip. And one thing, the advantage of combining the two inner terms is, one, for ease of calculations. Previous to this, there was various or numerous variables that needed to be determined for the deflection of the diaphragm. And the other advantage of incorporating the two inner terms is the incorporation of this apparent shear stiffness, G sub A. And this will allow a designer to extend your calculation to a variety of diaphragms, different types of diaphragms, not just wood structural diaphragms, and then also for unblocked diaphragms. Whereas the four-part equation was only for blocked diaphragms. And so that's the great news about the going from a four-term equation to a three-term equation. Now, for those of you that are die-hard four-term equations, it is in the commentary of the Wind and Seismic provisions, if you're interested. But again, that is only for block diaphragms. And when we transitioned from a four-term to a three-term equation, you can see that this is a chart on the right-hand corner of the slide where the three-term equation is a linear equation, straightens that out, whereas the four-term was a non-linear term equation. But as you can see, at strength level forces, 1.4 ASD, the two equations are identical. And then in between 0 to the strength level forces, we would see that there is a difference of 0.045 inches, but it's really very little difference between the two equations for those that are interested. Now, if you're interested in the 2008 commentary, and Buddy, you can fill me in later or answer this question later, but in the commentary of the 2008, there is an actual design example of mid-span diaphragm deflection. I believe it's going to be in the 2015, and Buddy can tell the audience later if it is. The commentary is being developed right now. Okay, now we're looking at the capacities. What do? We got to design. We have a demand on the diaphragm. We go to table 4.2 to get our nominal unit shear capacity wood diaphragm values. And I mentioned nominal because these values this table is to be utilized for both ASD and LRFD. And you'll note that there's also two sections. There's in section A for seismic and a section B for wind. And the seismic includes the apparent shear stiffness values as well for both OSB and plywood. Now, you'll also note that these tables were developed based on applying a 2.8 factor to those values that were in the legacy IBC. And that has to do with what the panels are based on. The performance PS2 and PS1 are developed, and these guidelines are used for manufacturing the panels. And this is a safety factor that is incorporated into those performance standards of 2.8. So that's applied to the IBC legacy values. So you multiply it to get it into a wind nominal unit shear value. And then just the straight ratio from wind to seismic design is 1.4, which is typical 1.4 value. So if you did the for example, for a 6 and 6 and 12 wind resistance of 520 pounds per linear foot, you divide that by 1.4, you would get the seismic value. But this is for, we included the two different sections just for ease of design and obtaining the values. Now, as I mentioned, those values are nominal values. There's a footnote in the table that states that you need to see this section 4.2.3 to change the capacities into an ASD or an LRFD value. You divide by 2 to get it into an ASD, and you multiply times 0.8, the resistance factor 0.8, to get it in an LRFD value. And that was true, no changes to those tables from 2008 to the 2012 or 2015. In addition to the capacities, there are some criteria for the aspect ratios of the diaphragms, which is listed here under table 4.2.4. Now we'll see where these aspect ratios are going to become more stringent when we get into looking at torsional irregularities or open front diaphragms. But these are the basic ones if you aren't torsionally irregular or if you're not an open front diaphragm. There's been a slight revision to, or actually clarification for the unblocked diaphragm, and that is a clarification of the notes where, if you can see the highlighted note that says panel edges. Before, it used to say members, and there was some confusion that that meant that the nailing of not only the members to the framing member to the panel edges, but also to the field nailing needed to be decreased from 12 or whatever it is to 6 inches on center. So this is just a clarification that we're talking about at the panel edges, and we're not talking about field nailing, that it is at the panel edges. So slight change, slight clarification. Now you also note when you look at your tables is that the illustrations for the configurations of the diaphragm has changed. And this is just to make it more clear. We've grouped case 1 and 3 and case 2 and 4 and grouped case 5 and 6 together to make it more clear to illustrate that the capacities of the diaphragms is dependent on the direction of load relative to those continuous panel joints and to the framing members, and it is not dependent on, it's independent of the panel orientation. And I'll give you an example. For example, here where we have case 1 and 3, we have a load in the east-west direction. The continuous panel edges on load case 1 and 3 all have the continuous panels in the, well, you can see in the illustration. And then also, independent of the orientation of the panels, right below it, you can see the panels are oriented 90 degrees so that, but the continuous panel edges are in the same direction, and the framing is in the same direction. So this clarifies it a little bit more clearly. Okay, now we're getting into, this is one of the areas where we've had some, I don't want to say major, there's more clarification of the language and a change in the overall horizontal distribution of shear section of the wind and seismic provision. And this is important because we need to understand how the loads go from or transferred from the diaphragm to our walls, whether it be by tributary area or by the stiffness of our vertical lateral resisting system. Now, we talked about idealizing a diaphragm as either flexible or rigid. ASC has some provisions that give you prescriptive provisions, meaning it's a recipe. If you meet these provisions, you can categorize it right off the bat as a flexible diaphragm. For example, if you're a 1 or 2 family dwelling, or if you have less than or equal to a 1.5 inch concrete topping and a certain framing, light frame construction, you can categorize it as a flexible diaphragm. In addition to that, you can also calculate the deflection of your diaphragm and your shear walls, and if your diaphragm deflection is greater than 2 times your average shear wall deflection, then you can idealize your diaphragm as flexible. Then that will inform you that yes, I meet one of these criteria, and I can transfer the load to the shear walls based on tributary area. The other method is idealizing it as rigid. Similarly, there's some prescriptive method in ASCE 7 that states if you meet this criteria, you can idealize it as rigid. However, in ASCE 7, prescriptively, there's no way for a wood diaphragm to meet that criteria as rigid because it requires it to be concrete or concrete over metal deck. There's no provisions for a wood diaphragm to prescriptively meet the rigid criteria. Okay, then you also have a calculated method of determining if you are rigid, and that is that your diaphragm deflection is less than or equal to 2 times your average shear wall drift. And then you can transfer the loads based on your lateral stiffness of your vertical lateral resisting system. Now beyond that, let me go here. What is new to wind and seismic provision is the envelope. And that is that you're treating, if you can't idealize it as flexible and you can't idealize it as rigid, you're semi-rigid. And that is analyzing something as a semi-rigid diaphragm is a complex analysis. And I'm not sure many engineers actually analyze it as a complex through these difficult calculations to determine a semi-rigid analysis. What we've introduced in the wind and seismic provision is the envelope solution, and that is where you analyze it as flexible, you analyze it as rigid, and you take the governing load to those shear walls, you're over-designing it by a little bit, but you're taking that envelope solution to analyze that structure. Okay, now once we determine whether or not we're flexible or rigid, there are other parameters that we need to look at, and that is torsional irregularity that can occur in a diaphragm. There are provisions in ASCE 7 that also need to be taken into account. The provisions here don't exclude those, or in other words, there are other provisions that need to be met. These don't trump those, but if that's the right word, but you need to consider both. For torsional irregularity, and seismic design category A is exempt from these, considering for this torsional irregularities parameters. If you're transferring loads in a torsional irregular system, the diaphragm needs to be analyzed as either rigid or semi-rigid. I mean, because it makes sense. How is it going to transfer the loads to those vertical lateral resisting system without having some stiffness to that diaphragm to transfer the load? Now, for those diaphragms that are torsional irregular, the wood structural panel diaphragms, the aspect ratios are reduced to L over W needs to be less than 1.1 to 1. And then for diagonal lumber diaphragms, either single or double layer diaphragms, that aspect ratio is 1 to 1. And for those that are torsional irregular, there's a check that needs to be checked, and that is that the story drift, the maximum story drift at A, needs to be greater than 1.2, the average of A and B. That's your check for checking if you're torsional irregular. And the one thing that the language in the wind and seismic provision has clarified is this specific check here is that it does state that you need to check the story drift per this equation. Previous to this, there was some language that stated that if the structure could tolerate the story drift, then you're okay. Well, what does that mean by if it could tolerate? Does that mean, oh, it can move and we're okay? Someone just says it's okay. Now there's an actual method of measuring if you're okay by checking the drift. So that's a clarification that is incorporated. Now, as we work through this, we have torsional irregularity, and then we have open front diaphragms. What you'll see with the provisions now in the wind and seismic provision is now there's a hierarchy in the criteria for different types of structures. If you're torsional irregularity, your aspect ratio is a little bit more stringent than a typical building. If you're an open front diaphragm, your aspect ratio is a little bit more stringent than a regular square box that has shear walls on all four sides, no irregularity. Then the aspect ratio is a little bit different or more stringent. And then if you have open front and you're torsionally irregular, then your aspect ratio requirements and detailing and all of that included, then how you analyze it is a little bit more even stringent. So there's a hierarchy because of these different irregularities that occur or different configurations. You'll notice that these illustrations show you a little bit different than what was in the previous wind and seismic provisions. Illustration A and B were in the previous wind and seismic provisions in 2008, and you'll see that L prime is the depth of the diaphragm and W is the width of the diaphragm relative to the direction of the force. What's new is, and to reflect what's really going on in the industry and how buildings are being built, is this C and D, and especially D, which reflects those. Many of them are mid-rise structures that have a long corridor throughout the center of the building, and then there can be an open front diaphragm. So we'll go into more detail on what is related to these open front diaphragms and the criteria related to this. So for open front diaphragms, if there is no torsion irregularity in that building, then it's similar to a torsional irregular building. The aspect ratio is, for wood structural panels, L over W of 1.5 to 1. And then similarly, diagonal lumber, single or double layer, is 1 to 1. Has to be less than 1 to 1. Now, if you're open front diaphragm and also torsional irregular, then the aspect ratio is even more strict. For those buildings that are over 1 story, it needs to be less than 0.67 to 1, and then for 1 story, you get a little bit of break of 1 to 1. In addition to that criteria, the similar criteria, in addition to the criteria I mentioned previously, you also need to check to make sure you meet the allowable story drift, ASD story drifts, which is that drift needs to be less than the allowable story drift at the outer edge of the building. So this provides you with a specific criteria that needs to be met on the drift at the edge of the buildings or the outer edges of the building. And it needs to be modeled as semi-rigid or rigid. In addition, some of you may be familiar with a 25-foot depth requirement. We've increased that to 35 feet. But the previous provisions not only had that 25 feet, it also allowed you to increase that to beyond that, and there was no upper limit if you met some if it met a diaphragm deflection that can be tolerated provision, which again, there was no definition of what that can be tolerated provision was. So now we've clarified what that is. It needs to, the maximum drift needs to be less than the allowable story drift, and the depth of your diaphragm has an upper limit of 35 feet. You can't go beyond that. And there's an exception to the rule. You can have a cantilever for those that have a 6-foot cantilever beyond the lateral resisting system. You don't, the vertical lateral resisting system, you don't have to comply to that 4.2.5.2 provisions. So you get a break for just a 6-foot cantilever. Also, if you're dealing with, for example, you're dealing with a garage that's only 1 story, it's not going to have as much of a challenge with resisting the load since it's 1 story, and as long as you don't have to meet the provisions of 4.2.5.2 as long as you're only 1 story, your depth of your diaphragm is less than 25, and your aspect ratio is 1 to 1. So you can idealize it as rigid without going through all the other criteria and distribute the load to the shear walls through torsional method. Now, on to high-load diaphragms, and we're almost coming up to the end of this section. But for high-load diaphragms, it was in the 2006 IVC, and it was introduced into the 2008 Wind and Seismic provisions. The high-load diaphragms provide you with almost double, maybe even double, the capacity of what you would see for regular diaphragms. You have, it looks similar to the typical diaphragm table, and it's a nominal unit shear capacities, and there's a wind section and a seismic section, but it also requires multiple nominal thicknesses, requirements of your framing members and depths, and there's lines of fasteners, not just one line. There's 2 or 3 lines of fasteners that need to be nailed, and it also requires special inspection of the diaphragm to utilize this method. And similarly to the previous load capacity, the diaphragm tables, we have a revised configuration of the figure that shows you the different load cases. And as I mentioned previously, it does require special inspection, and it does require a 3x minimum framing member to nail to, or 2 2x, and Buddy will get into that later, but 3. But there's been a clarification also in the 2015 in that a depth of the framing member, a minimum depth is required, and that is a 3x minimum depth. And this is also was in the IBC that made its way into the 2015 Wind and Seismic provision of the 3x. And here's an illustration that's in the Wind and Seismic provision of the multiple rows of nails. You can see in this illustration we have a framing member that needs to be 4x minimum because of 3 rows of nails, and we have the panel joint here and 3 rows of staggered nails on each side of that panel joint. And this shows you one of the reasons why we require a 3x a 3x minimum as opposed to a 2x minimum. When you get closely spaced nails, it can cause some splitting that can occur. So we have our last poll, I believe, for my section.
That is true. Sorry, I had trouble finding my little button. All right. Open front structures are limited to a maximum diaphragm length of blank in the 2015 Wind and Seismic. 25 feet, 35 feet, 50 feet, or open front structures are not allowed in the Wind and Seismic. All right. Several of you are already voting. That's great. Majority of you are already voting on one answer. I'm not going to give it away. All right, about 10% more I'm going to let vote. Hurry, hurry before I close.
That may have should have said maybe over 1 story, but I think the audience will get this answer.
All right.
You said it correctly because you read the slide. It should have been stated probably different.
Okay. All right, well, I'm going to go ahead and close now. And then share the answers. All right, 68% of you said 35 feet, 21% 25 feet, and then 9% said 50 feet, and none of you believed that they are not allowed. So, all right, and Michelle, I'm going to go ahead and let you share the real answer.
Okay, and the real answer is, let me say, drum roll please, 35 feet. And this applies to those that don't meet the requirements of the 1 story, but it's for those 35 feet is the maximum length, the depth of the diaphragm. So thank you very much. We'll transfer over to Buddy.
All righty, here we go. All right. There you go.
Okay. Thank you, Michelle and Marcy. And we'll transition now into shear walls and then leave some time at the end for some Q&A. So as we begin the discussion of shear walls, some of this will be very similar to what Michelle shared earlier, and the deflection equations that are used for shear walls are comparable. The three-term equations are what are shown in the body of the document, and the four-term equations are also included in the commentary. One change or relatively new provision for structural fiberboard shear walls is an additional reduction that was incorporated because of some additional review of testing, which revealed that we needed to be a little bit more conservative with the structural fiberboard shear walls. So make note of that new reduction there, H over B to the 1/2. Again, similar to what we discussed earlier, what Michelle discussed earlier with the diaphragm capacities, shear wall capacities are developed in a similar fashion, and so the result is similar capacities to what were shown in the legacy IBC tables that contain those values. And we've had several questions from folks about the fact that the nail shear wall and diaphragm tables have been moved from the IBC into the special design provisions for wind and seismic. That was done intentionally a couple of code cycles ago. The thought was that the ANSI consensus process and the standards development committee, the Wood Design Standards Committee that develops this standard, is a more rigorous process than the code development process. If you've ever participated in a code development process, in many cases the changes are debated for about 5 to 10 minutes because of the volume of changes to all the different code provisions. And so the anti-consensus process gives us a little more rigorous approach to developing these standards. And so folks are also wondering why are the staple values still in there? The staple shear wall and diaphragm values going to make their way into the wind and seismic standard, and that's unknown at this point. Part of the issue is that there are no ASTM fabrication standards or tolerances for staples like we have for nails, and so the other thing that we'll talk about when we get closer to the end is the fact that there are evaluation service reports as well for stapled shear walls. And so at this point the nailed shear walls and diaphragms are in the wind and seismic standard, and the stapled shear wall and diaphragm provisions are still in the IBC. But again, similar to what Michelle mentioned for diaphragms, there's an ASD reduction factor of 2, LRFD resistance factor of 0.8, and so we can't stress enough that the values, the design values shown in the wind seismic standard are nominal values. They are neither ASD values nor LRFD values, and so you do have to take an additional adjustment factor to those values prior to the design process. And this slide just gives an indication of how that works. We also had some questions along the way about the load factors and how that impacts the design. And so based on these ASD and LRFD reductions in the load factors that are used for LRFD versus ASD, you do see a benefit, a strength benefit for LRFD of about 12% based on the load combinations shown here. And so that's, we've done our best over the years to calibrate the LRFD approach to historical ASD design provisions, but as the load standards and load factors are changing and all the research is going into that area, the LRFD load combinations, you will see cases like this where you do see some benefit to LRFD versus ASD. Note also that for shear walls sheathed on two sides, that and this is not a change again since the both the 2008 and the 2015 wind and seismic standard are shown here. This applies to both, but this deals with two-sided shear walls and nailing to opposite sides of the shear wall. And so this footnote 6 states what needs to be done, but it's, if you're like me, it's easier to see it with a picture. And so where you have adjoining panel edges and the panels are staggered on opposite sides. So here's a panel joint here with nailing, but the other panel joint on the other side is here, then 2x framing is acceptable. The problem is if you've got adjoining panel edges here and here on opposite sides on the same framing member, the thought is that, and test results have shown that it creates potential for a lot of splitting because you've got so many nails then into this framing member. And so when you have a case like this, if they're not staggered, then you're going to have to go to 3x framing. So that's the sort of the illustrated version of that footnote 6. Unblocked shear walls are also possible, and again, this is not a change, but we want to point out that if you do have cases where you've got unblocked shear walls, and another question that came in while Michelle was teaching had to do with laying up panels horizontally versus vertically, and we understand that that is a sort of a regional preference. I've heard that in North Carolina, for example, they like to lay the panels up horizontally on shear walls, and so unless you block the edges of those horizontal panels, you'd have to use this unblocked shear wall adjustment factor. And you can see based on the numbers here that you can get as much as a 60% reduction in capacity if you're at 24 inches on center. The normal 16-inch on center has a reduction of about 40% for a 6 and 12 nail spacing. But it is possible to use unblocked shear walls. There is a 16-foot height limit and a 2-to-1 aspect ratio, but it has been tested and shown to work, and then that would not only apply to the strength of the panels and the layup, but it also apply to the stiffness as well. And so you'd have to account for that reduction in your stiffness calculations as well. So again, not a change, but just something we like to talk about and make sure everyone understands is if you are summing shear capacities and there are dissimilar materials on opposite sides of the shear wall, you're either going to take 2 times the smaller nominal unit shear capacity or the larger nominal unit shear capacity on one side, whichever is greater. But there is the exception for wind design, that the wood structural panels and gypsum on the opposite side are additive in that case. And so that does give you an additional benefit in high wind zones where you're able to account for the gypsum on the opposite side of the shear wall. Now, something new for the 2015 version of the Wind and Seismic provisions has to do with shear walls in a line. And in section 43341, the default provision there is this distribution based on relative stiffness or equal deflection approach, as it's sometimes referred to. And while this concept is not new, there is a new exception to this provision that should be helpful, and it's a simplified approach. So the exception that shows up now in the 2015 standard allows this simplified approach, which permits a distribution of shear in proportion to the nominal shear capacity of the individual full height segments. And that's provided that certain requirements are met. For wood structural panel shear walls, this distribution of shear is permitted, provided that the nominal shear capacity is adjusted by this factor 2b sub s over h for wall segments with aspect ratios greater than 2 to 1. And this factor is based on reduced stiffness observed from testing, and it provides roughly similar results to that equal deflection calculation method for a reference wall line configuration comprised of a 1-to-1 aspect ratio and a 3-to-1 aspect ratio. But what I want to show you here in this table is that that reduction for a 3.5 to 1 aspect ratio is about 0.57. And I also want you to note in your slide there was a little bit of a typo there on page 87. That should be V sub S times this reduction. So that's shown in red there. If you printed out a version and want to make a change to your printed copy, otherwise we'll revise this PDF and get it back up on the website so you have the revised version. But a common misunderstanding of this 2b over h factor, which was in a footnote in the 2008 Wind and Seismic Standard, was that it represented an actual reduction in unit shear capacity for high aspect shear walls. And the actual strength reduction associated with high aspect ratio shear walls is less severe, and we're going to talk about that in just a second in another section. But the 2b over h factor in this slide actually accounts primarily for stiffness compatibility of high aspect ratio segments. And so where this 2b over h is used to comply with the load distribution requirements in this section, the strength reduction adjustments don't need to be applied. And again, we're going to talk about that here in just a second. So the table that you're used to seeing in the 2008 Wind and Seismic Standard now has fewer footnotes, and that's because the footnotes have been moved over into the text, and that's where maybe some of these slides will help as we work through this. So this section 4342 has to do with new strength adjustment factors. And again, this is also new to the 2015 Wind and Seismic Standard. And this section contains these new strength adjustment factors to account for the decreased unit shear capacity of high aspect ratio wood structural panel shear walls. And you see, well, and it also applies to structural fiberboard as well, but you see the two different equations there, one for wood structural panels, one for structural fiberboard, and the related aspect ratios. as we talked about earlier, where the distribution of shear is based upon that simplified alternative adjustment factor method, the 2B over H adjustment, you don't have to further reduce but there is the case where you have to make sure that the requirements of this section are in addition to the deflection compatibility equation that we talked about earlier. And so you check both and then use whichever one controls. And so you see here in this table that the reduction factor, not quite as significant as the one we saw earlier for strength, but or I mean for stiffness, but it is for 3.5 to 1 aspect ratio in the range of 0.813. So then we'll move into the perforated shear wall method. So the last slide we were talking about dealt with the segmented, the traditional shear wall method. For perforated shear walls, there is a similar approach, but these have also been revised in the 2015 Wind and Seismic standard. So in previous editions, where this high aspect ratio adjustment was considered, it was applied to the overall perforated shear wall capacity. But the revision to the 2015 allows that adjustment to apply only to the high aspect ratio perforated shear wall segments based on the stiffness compatibility considerations, as opposed to the overall shear wall. And so this will generally permit an increase in the design strength of your perforated shear walls where you're incorporating these high aspect ratio segments. So for example, if you have a wall where you've got, say, a couple of windows near the ends of the shear wall and a much longer full height segment between those windows, you're going to see an increase as opposed to the previous editions that penalized the entire wall. But if you have a series of windows where all your high aspect ratios segments are all about the same throughout the wall, then you're probably not going to see much benefit, because that adjustment is going to apply to each of those full height segments. So there is a little bit of a bump here that you should be aware of as you're working through the 2015 provisions. For the force transfer method, there's no real change here, and so you don't have to worry about that being applied here. When we talk about perforated shear walls, again, we want to make sure that everyone understands there is the tabulated approach where these values are shown and are used to adjust the shear capacity for the shear walls. And near the beginning of the presentation, Michelle showed a couple of examples. The benefit of this approach, this perforated shear wall approach, is that it allows you to move or to remove your hold downs from those interior openings. So if you have windows and doors around the or in the interior of your wall, you wouldn't need to have hold downs around each one of those window and door openings. You could put your hold downs at the corners, use this adjustment factor, and that basically bumps up the strength and stiffness of your wall. There is, however, an equation that can be used instead of the tabulated values that does give you a little bit of an advantage. And so if you want to program that equation, the advantage is that it doesn't penalize you for that full-size opening. So in the table that was shown earlier, it's going to assume the maximum opening. So this door, for example, would be the maximum opening in your perforated shear wall. It doesn't give you any benefit for these sheathed areas here below the windows. But the equation, on the other hand, and I'll jump back to that, does allow that because it actually allows you to calculate the percentage of openings in the wall as a function of the entire wall area. And so that gives you an additional advantage as well if you're not intimidated by the equation that we used. Slight modification or clarification in section 4.3.5.3 just clarifies which materials can be used with perforated shear wall design methodology. It clarifies that wood structural panels on one or both sides are permitted, as well as gypsum wallboard on the opposite side, of wood structural panels. And so just a clarification there for that particular slide, or for that particular provision. So I'll ask Marcy if she will come back and lead us through our next poll question.
Absolutely. All right. Maximum allowable shear wall aspect ratios are not included in the 2015 Wind and Seismic. Vary depending on the wall sheathing material, are independent of wall sheathing material, or vary depending upon the shear wall anchorage. All right. And I see most of you are already voting. Go ahead. All right, about 50% of you have voted. Keep going. About 10 more seconds. All right, and then I'm going to go ahead and close the poll. All right, 75% of you say that it will vary depending on the wall sheathing material. 12% says it's independent of the wall sheathing material. Excuse me. About 10% say it varies depending upon the shear wall anchorage, and 3% says that it's not included in the 2015 Wind and Seismic. All right, and Buddy, I'm going to have you tell them what the real answer is.
Okay. So the real answer, and I'm trying to get here, it is answer B. So 75% of you got that right. Very good. And
just, I'm going to interject here for just a minute and remind people that whether or not you've got that right, it does not impact your certificate or your CEUs at all.
Yes, thank you, Marcy, for that that clarification. Yeah, we get that question. I get that question a lot. So, okay, so let's move along then into some of the construction requirements in section 4.3.6, and this is just a slight modification or clarification, if you will, to let folks know that if you want to substitute two 2x members to replace a 3x framing member, in the 2008, that was buried pretty specifically in the wood structural panel shear wall section, and so we've moved that out ahead of that section so that it's clear that it applies not only to wood structural panels but structural fiberboard as well. Also clarified that the two 2xs can be substituted for a single 2x as well, and while that wasn't necessarily prohibited before, it's just clarified. Where that might come in handy is in a panelized wall system. If you're familiar with panelized wall construction, You know that wall panels can be manufactured in the factory, shipped to the job site, and then constructed on site. And so this provision then would allow you to stitch those wall panels together and keep that shear wall capacity intact along that entire wall, so you wouldn't necessarily have to build hold downs into each of those locations based on this approach. So this should help in the panelized system area as well. Again, not new to the 2015, but making sure that you know if you're used to using the IBC and you're wondering where those provisions are, adhesive attachment of shear wall sheathing has been rolled into the Wind and Seismic standard, so that's still there and shown in a table as an exception to this section of the Wind and Seismic standard. Again, not a change to the 2015, but just a note to make sure you understand that there is an exception to having a panel smaller than 4x8 at boundaries and changes in framing, and that just there are specific provisions that go along with that to make sure that your edges are blocked and you've got nailing for those smaller members. Again, to make sure you are familiar with the provisions for shear wall design, the new provision, or a provision that was added in the 2008, clarified that the 3x3 inch plate washers had to be within a ½ inch of the sheathed edge of the bottom plate. And so I'll show you here in a second some of the test results and reasons for that, but it was really to make sure that we didn't have cross-grain bending or tension perp that can occur right about the location of this anchor bolt here in that bottom plate. And so there are some exceptions that allow for lower capacity sheathing materials, or if there are hold downs in place that are sized for full overturning loads. But those 3x3 anchorage devices or anchorage provisions are required. A slotted hole is permitted, but again, that getting them within ½ inch of the sheathed edge is important. And for a 2x4 bottom plate, that is automatically satisfied, because that 3x3 you'd end up with about a ½ inch on either side, and so you'd be within that ½ inch requirement. But if you had a 2x6 bottom plate, you'd have to offset those anchor bolts or use that slotted hole to make sure that you get those plates, those 3x3 plates, to within a ½ inch. And whoops. Again, there are some exceptions here where standard cut washers are permitted, and if the anchor bolts are designed to resist shear only, and you've got hold downs designed for overturning, neglecting dead load, if your aspect ratio is less than 2:1, and you've got some nominal shear capacities less than what's shown here for seismic, then you could still use the round washers. So there are some exceptions there for some of the lower loaded areas, but otherwise the default is going to be those 3x3 plate washers. You can also install wood structural panels over gypsum. So if you have shear walls that also require fire resistance ratings, there are capacities specifically listed in Table 4.3b for wood structural panels applied over ½ inch or 5/8 inch gypsum wallboard or sheathing board. And so those tables are included as well. There's also a section that was incorporated in the 2008 Wind and Seismic standard, and we'll kind of give a brief overview of this, again, just to make sure you know what your options are. But you can use wood structural panels now to resist combined wind, uplift, and shear, or to resist tension only from wind uplift as an alternate to metal straps. And so this new section 4.4 was incorporated in the 2008. It's been carried over in the 2015. But basically what it allows you to do is once you know your shear wall design capacity of your sheathing, so you design your shear walls first, and you need a minimum of 7/16 wood structural panels to do this. But once you have your shear walls designed, and let's say that your shear wall in this first set of columns here required that you have 6-inch panel edge spacing and 12-inch field spacing, so 6 and 12. What this simplified approach allows you to do is determine how much additional uplift capacity you can get from your wood structural panels if you change your nail spacing at the top and bottom edges of the plate to 4 inches on center or 3 inches on center as shown in these columns. So if you go from 6 and 12 to 4 and 12, you get an additional 168 pounds per linear foot of capacity to resist uplift. If you go to 3 and 12, you get an additional 336 pounds per linear foot of capacity. And if you double up your nails along the top and bottom edges, and there are nailing provisions that we'll show you here and nailing details to avoid splitting that we'll show you, but if you double up your nails even at 6 and 12, then you could get additional capacity of 336 pounds per linear foot all the way up to an additional 1,000 pounds per linear foot. And so you see that for different types of shear wall nailing configurations shown here, and then what happens if you add additional nailing. And this is all based on testing that was done at APA, our sister association out in Tacoma, Washington. Vertical sheathing, minimum spacing of fasteners in a row is 3 inches. There's got to be horizontal blocking installed if the panels break intermediate to the stud height. But it does apply to all shear wall types. The individual full height segments, perforated and force transfer method. But the panels again have to be 7/16 and installed and can be installed with the strength axis either parallel or perpendicular to the studs. Here's that some of the nailing configurations that I mentioned earlier, and you can see when you get to that staggered nailing configuration as shown here that the spacing that's shown in the table is based on the spacing of each row of nails. So if you had 6 and 12 double nailing, you'd have 6 inches on center here, which is the equivalent to basically 3 inches on center staggered. So I think you'll understand if you look back at the table and then look at these drawings what we're talking about there. But you'll have to note the construction provisions that are incorporated as well. So one of the things that you need to be aware of if you're using this approach is that there is the potential to create tension perpendicular to grain stresses in your blocking. So let's say you lay up your panels and they break across a stud here at the mid-height or at some intermediate point, then you have to make sure that you account for any cross grain or tension perpendicular to grain that could occur in the blocking, because now you're resisting those uplift loads, tension, across this, this blocking. And so the details there that come into play include using sheathing, some wood structural panel sheathing that is the same thickness and makeup as what's used for the wood structural panels that are here on the exterior of the stud wall. And so that wood structural panel sheathing that's added to the blocking then takes care of that cross-grain tension that can occur here in the blocking. So, you know, there are trade-offs to this approach. Obviously, you now, with this approach, don't have all the metal straps that you had on each stud before, but you do have some additional blocking detailing if you end up with sheathing splices that occur at mid-height of the stud. So you have to talk that over with your contractors and builders to make sure that they're on board if you were to take on this approach. The next few slides, I'm actually going to just try and give a basic overview. I'll let you go back and look at those on your own in a little more detail because I want to leave some time for question and answer. But those sheathing, this table kind of shows where those sheathing splices would be required for one story versus multiple story buildings. So this is a handy little table. It's not in the Wind Seismic standard. And then we go through an actual example here of a multi-story example. I mentioned earlier that you got to make sure you avoid tension perpendicular in any blocking if your splice joint occurs across the studs, but you also have that same issue with the band joist where you're now transferring tension and it's perpendicular to grain across the band joist. So there are nail spacing limits here to make sure that you don't exceed tension perpendicular to grain allowances in your band joist. So there's some prescriptive limits that come into play there for single and double rows of fasteners. And so what you see here are where you could potentially have splices at mid-stud height. Again, special detailing provisions for the blocking there. And then this color, this key here shows where you're resisting uplift versus shear versus a combination of the two with your nails. So I won't go into any detail here with the example problem. It's something that you can take a look at on your own. We want to leave a few minutes for Q&A here at the end, but this is a pretty good example that you can work through. And we've covered this in other seminars as well, but I will point out that once you've got your rows of nails at the top and bottom plates, then you also need to go back and make sure that you've got enough nails in the interior of the panel to carry those uplift loads through the structure as well. So there is some additional calculation in addition to what you see here in the table, which covers the top and bottom of the panels. You have to make sure that you've got enough capacity here in the interior as well to carry those uplift loads. So this example problem walks you through that. The other thing that this provision allows for is where you could just handle uplift only versus combined uplift and lateral loads. So let's say, for example, that you do your shear wall design and you only need a couple of full height panels at the corners of your structure. You could use the panels in the interior of the structure to carry your wind uplift loads because those interior panels may not be needed for shear. And so this table allows you just to size those panels to carry uplift through the structure. What is new to the 2015 Wind and Seismic standard is the spacing of the anchor bolts for this approach. So as you can imagine, since we're carrying a lot more tension through the structure, there is a lot more potential for additional uplift and cross-grain bending on this bottom plate. And so in the 2008 Wind and Seismic standard, we prescriptively set the spacing for these anchor bolts to 16 inches on center. So if you're going to use this approach, you spaced your anchor bolts at 16 inches on center regardless. It was just a prescriptive approach. Well, we did some additional testing and analysis, and now there's a new table in the 2015 version that will get your spacing up from 16 inches on center all the way up to 48 inches on center, depending on your configuration. And so take a look at that new table 4.4.1.6, and that'll give you some relief for the anchor bolt spacing in those in this combined approach for combined shear and wind uplift. The other clarification here is that if you've got that sheathing extending to the bottom plate or sill plate, we now have minimum end distances for those bottom plates, and so in 4.4.1.6 paragraph 3 we've outlined those new end distances, and the provisions here sort of give you a sense of what those end distances are: 7D or less than half the tabulated value, or less than 12 inches on center, whichever controls. There are a couple of appendix chapters. These remain unchanged, but just so you know that we often get questions about what are these nail dimensions if I'm using pneumatic nails versus what you call out for common and box nails. What are the dimensions? And so Appendix A gives you the common box and sinker nail dimensions. You can use these to match up with your pneumatic nails. There are also some standard cut washer dimensions shown here that didn't show up anywhere else in the standards before. So I'm going to bring Marcy back, and we'll do, I think, what is our last poll question before we jump into the Q&A.
I believe it is our last poll question. And let's see, shear wall foundation anchor bolt washers must be not less than 0.229 inches by 3 inches by 3 inches in size. They must be placed within 1 inch of the sheathing material, both A and B, or none of the above. Go ahead and vote. There's one answer that is not getting any votes whatsoever, so, well, I misspoke. All right. 10 more seconds. All right, I'm going to go ahead and close the poll. Get your last minute vote in, and closed. All right, so 54% of you say that a shear wall foundation anchor bolt washer must be not less than 0.229 inches by 3 inches by 3 inches in size. 28% says it's both A and B. 15% say none of the above, and 2% say placed within 1 inch of the sheathing material. Okay, buddy, I have no idea. I'll let you tell the real answer.
All right, thanks, Marcy. The correct answer is A, and I know some of you might think, well, you know, it does have to be placed within 1 inch because it's got to be placed within a ½ inch, but the answer that we talked about earlier the real tolerance there is within a ½ inch of the sheathing material, and there are also some exceptions that we talked about that would allow for round washers, but as the default, it's the 3x3 inch within ½ inch of the sheathing material. So this is a summary slide, and if you're sharp, you see that it says top 10 changes, and then we have 11 listed, but you know, David Letterman does top 10, and that's just catchy. So I guess we could delete one of these, but these are the top 11 that we talked about today, or that are covered in the webinar. Also want to point out that just prior to today's webinar, that we were able to post a paper that outlines the changes to the 2015 Wind and Seismic standard. And so probably go there, open up the web browser here in a second and show you how to navigate to that. But we also have authored an article for the July issue of Structure Magazine, so it'll be showing up there as well. But if you want to go to the website, navigate to the 2015 Wind and Seismic page, you'll see an icon there that says what's changed, and you can download that paper as well. So, Michelle, I'm going to stop there. I think we've had some questions come in, and I see Brian has already posted the link to that paper there in your chat box. So if you want to get that paper downloaded, you can click on that link right in the chat box and navigate there. So what kind of questions came in while we were talking here, Michelle?
Okay. Just wanted to point out one thing you touched on is the icon of what's changed throughout our website. We have those icons on, and if you click on that, you'll get information on past changes also for the NDS and other publications. Now, for the questions, we had a question that came in is regarding the blocking and what's the minimum depth requirement for blocking for diaphragms or shear walls, and can you use a flatwise blocking?
Yeah, and you may have to help me out on this because this was over in the diaphragms section.
Right.
I believe the minimum is 3x for the high-load diaphragms.
Right. And then for the shear walls, if you're using horizontal, as I think you mentioned this previously about horizontal panels, for the blocking of that, it depends on the nail penetration requirements in the table, which lists the minimum penetration requirements.
Yep, that's a good point. And once you add and if you're using it for combined shear and uplift, you saw the details for adding the wood structural panel sheathing to the blocking there, then you'll likely meet those minimums. In that case, you have to go with your blocking horizontally to leave enough room to get that wood structural panel sheathing in there. So. So to, I think, summarize, Michelle, what you said is true. If you have a nail penetration requirement, you'd have to go with the strong axis for your nails. If you can meet the nailing penetration requirements, you could lay it up horizontally. And then if you're going with the combined shear and uplift, you'd have to go with horizontal blocking.
Right.
Or flatwise blocking, I guess.
Can you give a little bit more information regarding panel edges as far as instead of a 3x, 2 2x's and connecting the two?
Yeah, so that provision or exception as it's written now states something to the effect, and I'll just turn there in the Wind and Seismic standard. By the way, I don't think we mentioned while I'm turning there is that if you aren't already aware, you can download a free view-only version of the 2015 Wind and Seismic standard from the website. It's a non-printable version, but you can download and view it. And so If you haven't done that yet and you're interested in taking a look, again, navigate to the Wind and Seismic page to the 2015 edition. You can download that free version. You can also purchase a printable version if you'd like to print out a copy. But in section 43611 of the Wind and Seismic standard, it says that you can substitute two framing members that are at least 2 inches nominal in thickness, provided that they are fastened together with fasteners designed in accordance with NDS to transfer the induced shear between members. And, and then further, if the spacing, the nail spacing ends up being less than 4 inches on center, you have to stagger that nailing.
And I believe the at least the 2008 has some commentary language on this as well. Probably in the 2015, I would think so also.
Yes, yeah, it does. And speaking of commentary, that's also being developed now. It's out for final review with our committees, and once we get that fully reviewed and typeset, then that'll be incorporated into the Wind and Seismic standard, and at that point it will upload it to the website, and if you've purchased a printable version, you'll get a notice to download the new version, and then we'll also then begin printing copies for sale at that point once the commentary is complete, which it almost is. I saw a final version just last week. So
great. Another question came in. I think this has to do with the diaphragm or the section on torsional irregularity. It states, what can cause torsional irregularity? And for seismic, it could come into play when you have building configurations where the center of rigidity is offset, your mass is offset from the center, and also if your shear walls, if you have a stiffer line, a whole line of shear walls on one side of the building and only one shear wall on another side, that can cause torsional irregularity in your resistance of the lateral load.
Right, and the new figures that were added are intended to kind of help clarify some of those cases, like a cantilever diaphragm or some of those corridor type structures as well.
Mm-hmm. Okay, another question came in regarding shear walls with dissimilar materials and resisting seismic load, if that's allowed, to have wood structural panel on one side and gypsum on another. And
for seismic, that is not allowed. And so that is only, or you only get credit for it. Let me put it that way. You can put gypsum there, but you're not going to get credit for it. You can't use the capacity for the gypsum. That's only permitted for wind design.
Isn't it depending on your seismic design category? Well, it also is depending on where the building is, and if it's in seismic design category, you know, what seismic design category, but it will affect your R value also if you're using gypsum as opposed to wood structural panel.
Yeah, it does. But based on the capacities that are shown, that the additive part of that is only for adding wood structural panels, and gypsum is only for wind loads.
Okay. Let's see. What else do we have? Someone asked about the when were shear walls last tested for nails, and where can I see the tests? They've been the last shear wall that we're aware of is the cyclic testing of unblocked wood structural panel shear walls that were recently tested, and it's you can find an article or a white paper on the testing in Wood Design Focus, summer 2014 issue.
Yeah, and I'm going to navigate to a section of our website too called Free Publications. And I just want to scroll down here on that page to some of the what we call technical documents by others. So the some of the shear wall tests that have been run are shown here under that section where you can just go and download them directly from our website. And so take a look at that. Again, that's under Publications, Free Downloads.
Going back to that dissimilar materials, I thought it was if you have gypsum that's less capacity than wind structural panel, you would take 2 times the lesser, and then you would have.
Yes, you're right. You're right. Good call, Michelle. Yep.
Yeah. And then you would have a reduced R also.
That is correct.
Yeah. And then someone was asking about, this question came, I think you addressed this question, but it came up again. Staples versus nails. Why aren't staples in the Wind and Seismic provision?
Yeah, and there just aren't as many or any standards for staples as far as manufacturing tolerances. Most of those are proprietary products based on the manufacturer of the power-driven the power-driven device that's used to drive the staples, and where we have ANSI or ASME standards for nails and other fasteners, there just aren't the same types of standards that give us an idea of what the material properties are for the staples themselves. And so IBC continues to carry those. I think as the standardization process continues to evolve, you may eventually see that in the wind seismic standard, but we're still kind of waiting on a more generic standardized approach before we go that route. So.
Yep. Okay, I think we're at the hour. Up at the hour. Does Marcy want to close us out?
Absolutely. All right. You've got my slides for me?
Yes.
And the one thing I would suggest, I know Marcy's going to mention about surveys. For those of you, we really appreciate your feedback on the surveys, but one question I would ask is, would you be interested, or do you know of people that would be interested in presentations or education on basic design of wood structures, just overall basics? This is pretty intensive engineering for this session, but overall basics. And then I'll hand it off to Marcy.